Okay, so let's talk a bit about finding a compensator. So I want to design a G sub C for a given system. What do I need? I need to know what the plant is. That's one thing. I need to know what the system configuration is. And most of the time, this will be the standard configuration. If it's not given to you, at least for my class, it will be the standard configuration. And remember, that is our usual GC, GP with the negative feedback loop, just like so. Negative feedback right there, plus, and we have our R and Y coming in here. Okay, we can add our OT. So, okay, so that is the standard configuration. I could specify another one, and if I do, use that one instead. Okay, the last thing that I need to know is exactly what are we trying to do with our GC that we want to design. So we could be doing something like stabilization. Okay, do we want the output y of t to go to 0 and stay there as t increases? Do we want to compensate for some kind of a disturbance that's coming in? By the way, the disturbance would be added in right there if we had one. Okay, would also be an input to the plant just along with the control signal. Do we want to have our output go to some specified set point and stay there as t increases? Or do we want to have our output track some control signal? Sorry, not control signal, a command signal here. We could do that, or we can do any combination of this one, this one, this one with a disturbance. Okay, so these are the different cases that we'll cover. So let's talk about the simplest case, which is just stabilization without any disturbance in place. Okay, so let's say I give you some GP. So for some pre-specified plant transfer function that's given to you, design a compensator block right here, GC of S, to make the closed loop system response or output, either one, same thing, y of t go to 0. And that's always with the caveat and stay there as t increases. Okay, now we could further refine that, just a note, and say not asymptotic stability here, just increasing t. Don't necessarily care when I get there as long as it gets there, but we could specify by a specified t. That's a different problem, and so we could do something like that. For right now, let's just stick with the asymptotic case. Okay, so what am I going to do? I am going to, first of all, find my GCL, my closed loop transfer function. If I don't already have it, you probably will memorize the one for the standard case because we use this so much. And once we have this, from here, what we want to get is the QCL, that polynomial on the bottom. So remember, we have a polynomial on the top, PCL, and that specifies our system zeros. What are system zeros? They are the roots of this polynomial, but they also specify critical frequencies. The QCL gives our system roots. They are called system poles. Now the system poles are really interesting. Those are what determine the stability or instability of our system. By solving this polynomial, that's how we determine if the system's stable or not. So this one is very important right now for when we're designing our G sub C. So what we want to do is get this equation. Now, if we are dealing with the standard system again, you probably know this one by memorizing it. You use this so much that you're probably going to know that this is P sub P, P sub C, plus Q sub P, Q sub C. And if you're wondering, how did I know this? How did I know this equation? Well, in another video, we were talking about how to find the GCL, and we actually derive this equation right here. But in general, the way we get this is from finding the GCL, which is the equivalent of this entire system, as one transfer function, and then we will plug in the PC QC for our G sub C, and for our G sub P, we also plug in P sub P over Q sub P. Okay, we make that, substitution, we reduce it, and we are left with a polynomial over another polynomial, which is our PCL over our QCL. And this is the equivalency for our QCL. This is the expression right here. Okay, so it's really handy to know this, and then you can just make these substitutions, because we will know what our GP is. It's part of our problem. These are one of the things that we need to solve the problem if we're going to design a GC. But GC is something we're going to be trying different designs for, and so to be able to really quickly plug something in, see if it works by our necessary sufficient conditions, that's really, really handy to do. All right, so in order to do this, let's use an example. We'll do something pretty simple that we've done in class. So we talked about this already, but let's do a real quick example just to review this technique. Okay, so how about something like the double integrator? Double integrator, something like that right there. Okay, so, and a quick review, we're talking about going from time domain over to Laplace domain. We can do this. Oh, sorry. That should be an S. 1 over S squared. Okay, this is our GP of S for that system. It's 1 over S squared. Okay, so what I did here is I took a time domain system. If you're given the equation for the system model, kind of like this. By the way, our natural system is just this. Okay, for this problem, we have no disturbance, so this is our natural system. Once we place in the controller, we have the U right here. If I wanted to find the transfer function for this, I would just stick in any kind of variable. I could go ahead and use the U, that would be fine, but our natural system actually does not have a controller in it. Remember, the controller is something that we design. We put it there, it's not part of the existing system as it is. So, natural system just off to the side, know that. We put in our controller, we find the or any variable, find the transfer function by bringing it over to the Laplace domain. Remember, a derivative in our symbolic Laplace is envisioned as a multiplication of an S. An integration is a division by an S. So bring that over and then develop the transfer function just by dividing through output over input. Okay. All right, so this is our GP right here. All right, so what in this case, what is our p sub p? It's 1. And our q sub p, s squared, okay? And if you know where we're heading like with all this stuff, we've already discussed the concept of free s's, and we'll get to that shortly. In this problem, we'd have 2 free s's. So anyway, so GP is here. Now what we want to do is design a GC in our problem, back up here, back up just a little bit. We want to stabilize the system. So what I'm going to do is take a couple of trial designs for GC. Now we're just going to follow a pattern to find the minimal order GC, okay? So what we want to do is start from the least possible complicated case, and that would involve no s's on the top. So we'll just have some kind of a gain divided by 1. Because I want to express this as a polynomial over a polynomial, I'm writing it over 1, but it really is just this gain KC that we design. So I want to see, we'll label this trial design number 1. What I want to see is, does this work? If I use this trial design, can I stabilize the system? So what we're going to do, once we have our trial design, is plug that into our QCL equation along with our GP and see if we can, by way of necessary and sufficient conditions, stabilize this. All right, so that means, just plugging these in, QCL is going to be P sub P, which is 1, times P sub C, which is KC, plus Q sub P, which is S squared, times Q sub C, which is a 1. All right, so I've got S squared plus KC equals 0. So can I stabilize this? Well, if I were to, let's just do an example and see, because this could be a little bit confusing here. If we plug in KC, let's see, for example, KC equals, let's say 4, and I plug that in, I've got S squared plus 4 equals 0. And now, if I were to solve this, and let's say solve for s, find the roots, I have s squared equals -4, which then solving that, I would have an s equals plus or minus the square root of -4, which is equal to plus or minus 2j. So in this case, this is actually on the axis. It's on the imaginary axis. I have a plus or minus. It's going to be marginally stable. It's not going to be stable. If I have the ability to design something that can be stable, or if I have the choice between a marginally stable and stable, stable is way, way better. And marginally stable is not bad because it's bounded, but now you see the difference though. So let's keep going. Let's just mark, you know, if I've got nothing better, if I can't do anything better, I can come back to this, but it's not as good as a fully stable case. So let's try for the fully stable case. All right, so if you remember, just now as we're discussing, GC, our first trial design, I want to write these out here so that we can kind of see the trend. GC of S equals to KC over 1, and that'll be our trial design number 1. Number 2, GC of S is equal to KC over S plus A. Okay. All right, so I increased the complexity here, and I increased it by adding an s plus some term on the denominator. Now, the question might be, why did I not put this on the numerator? I didn't put this on the numerator because remember we have to satisfy if we have a P over Q for some given transfer function. The P is said to be of mth order, Q is of nth order, and to build this in the real world, we have to have that n is greater than or equal to m. M just cannot be bigger. So if I were to add the s term on the numerator, we would be violating that rule right there. I want to adhere to this. So when I have the order of the numerator where I'm able to afford putting something on the top, I want to do that, but I don't want to increase the order of the numerator beyond what the denominator already is. Hopefully that makes sense. Okay. Also an important note, you definitely don't want to increase the order of the denominator beyond what you absolutely have to. Every time you increase the order of the denominator, you are going to increase the order of this QCL equation that we're going to find. This is going to be one order bigger that you have to solve for the roots. So I don't want to do more work than I absolutely have to do, so I'm not going to increase this order beyond what I absolutely have to. Okay, but let's try trial design number 2 here. Now, back, we're looking at our QCL equation right here. We're just going to plug this right back in. GP is given to us right here, so we know what QP is already. It's s squared. Okay, so we'll keep that handy. All right, so let's plug in and find our QCL. All right, so QCL, first we're going to start off with the P sub P term. So P sub P for this equation is s squared. All right, so, oh, I'm sorry, that's actually 1. So it's, we multiply by 1. Okay, next one, P sub C. Now for our GC, that's actually KC again. All right, just like so. And then we find our QP right here. That's s squared. This doesn't change. This equation doesn't change throughout the whole problem. Okay, and then finally, we have our Q sub C, S plus A. Okay, so we found this equation. Let's multiply this out. We have a KC plus S cubed plus A times S squared. Okay, and if I write this in the correct order, oh, actually, sorry, that's an A. Got ahead of myself. The 0 for the S term, and then we have KC. Let's try to solve that right there. Now, you know from the necessary sufficient conditions that you really want control over this term. Now, we could talk about stability by factoring out the S if this term had an S. And I could factor out an S and then I could work on stabilizing everything else. But that's not the case here. I have a KC without an S, so I have to have this term right here, okay, to ensure that I have stability. And to illustrate just a little bit further and possibly make this a little clearer, let's write out these necessary sufficient conditions. You know that for a cubed equation, third order system like this, we're going to have, and this is an A again, try to make that a little clearer. We're going to have that A is greater than 0, and that whatever this term, we'll call that a B1. Okay, B1 normally would have to be greater than 0, and then we would also have to have that A times the B1 be greater than this KC term. Okay, so, and of course these being positive come because we have a Monich equation. This is already a +1. So everything else has to be positive. Okay, so knowing all of this, this can't be stabilized. We don't have a B, or rather B1 is 0 in this equation. So this control, or this compensator design is not going to work. We need another trial design. Let's try our third down the order. And so how we're increasing the complexity, I added the s plus a term down here. And for this one, since I have an s plus something down here, I can actually add an s term to the numerator. So let's do that. Let's do s plus b up here. Okay, just like so. Now, let's go ahead and do the same thing. So this was trying GC2. So this didn't work, so let's try GC3. All right, so GC of S number 3, and QCL in this case. All right, so remember the equation. QCL, it's a P sub P, P sub C, so we'll get that out first. Our P sub P is 1. Our P sub C that we're looking at here is going to be this KC S plus B. Okay, so we'll get that out. And in our next term, for the QCL, we have a QP times QC. All right, our QP is S squared, and our QC is S plus A. So we multiply by S plus A. Okay, so let's go ahead and multiply this out. KC times S plus KC times B. All right, and multiplied this second term out, that's actually 3 S squared times S, that's S cubed, plus A times S squared. Okay, so let's write this in order. S cubed plus A times S squared plus KC times S plus KC times B. And if we solve this, set it equal to 0. There we go. All right, so let's re-examine our necessary sufficient conditions. We have an A greater than 0. So I'll just write these out below. We have A greater than 0, and next coefficient is this KC. We want KC to be greater than 0 as well. And then we have this last one right here, and we have to have that KC times, KC times B has to be, let me write this out a little clearer so we can keep this trend of something greater than something. A times KC has to be greater than KC times B. Now, for our equation, we can reduce this. We can cancel out that KC. A has to be greater than B. Okay. And again, these are positive because we have a monic equation. This positive 1 coefficient right here that we don't have to write out, but we know that it's there, that sets the positivity of our necessary and sufficient conditions. Okay, so can we choose, since we can choose A and KC and B, can we choose values that obey these equations? And it turns out that, of course, yeah, we can do that. Say, for instance, that A is equal to 10. KC, let's say, is equal to 9. And I'll make B equal to 4. Does that work? Do these three equations, here, here, and here, do these show up, are these valid, are these values valid per these equations? And yes, 10 is greater than 0, KC 9 is greater than 0, and 10 is greater than 4. That works. Now, there's no reason that I specifically chose 10 or 9 or 4. I just tried to choose something that would work with these equations. And you can do that as long as the problem statement is such that you're allowed to choose whatever values. You're not supposed to use ITAE specifically. You're not supposed to set specific roots. You can do that, and that is fine. But let's do something where we are using specific values. Okay, so let me just repeat this QCL. I've got QCL, I'm just rewriting the equation that we just came up with. S cubed, A times S squared, KC times S, and KC times B equal to 0. All right, so what if I wanted ITAE choices? Okay, so in that case, you would look up in the ITAE table. Of course, I would give you an omega sub n natural frequency value. Let's say like here, I made it equal to 1.0, something like that. You would plug that in and you would get that polynomial, and you would use the row that corresponds with the S cubed, and then you would write this out and set these equal to coefficients, whatever this is, times S squared, whatever this is times S, whatever this is right here, times S to the 0, okay? And that's how you would do that. Also, what if we wanted to have a specific set of system roots, whatever they are? Let's say specific lambdas. Let's say I gave you, I want the system roots set to specific lambda 1, lambda 2, and lambda 3. Okay, these are all symbolic, and I don't think that we've done a case like this before. Of course, if I gave you like -4, -5, -6, you could just plug these in with what we're about to do. What you would do is say, I would like to expand this right here and once I FOIL this out, you'll get a lambda cubed plus some coefficient lambda squared plus some coefficient lambda plus some other coefficient lambda to the 0th, which is 1. And then you would do the same thing here. You would set this value, this A value up here equal to this coefficient here, okay? So that would be the same thing. So specific system roots desired. Okay, so those are the two main design procedures. Once you find a G sub C that works, and you can satisfy those necessary and sufficient conditions like we were just looking at, you can either use, depending of course on the problem statement, values that just work to satisfy those equations. That's designed by necessary sufficient conditions, or ITAE choices of the system roots, the optimal roots, or specific system roots, okay? And again, by setting these system roots, we are setting actually the closed loop system poles.